Hello everybody. In this talk we're going to be talking about big O notation and what it means. So big O notation is incredibly important inside of the fields of computer science because it gives you an estimate of how things grow over time. So if I was to look at a plot, again, forgive my drawing, but if I was to, draw out some sort of function that looked like this and it trended off that direction towards infinity, and then you were to say, oh, well, how big is this function, or how does it grow over time? You might be inclined to say, okay, maybe it looks like an exponential graph, in which an exponential graph goes kind of like that. And maybe you might be smart enough to say, well, it probably isn't, like a line, because a line would look something like this. So that's what big O notation is all about trying to explain. It's trying to say how does our function that we're trying to look at, in particular this one right here, how does it grow over time? And we're going to apply some sort of a mathematical definition to this. So what do we want to know? We want to know, actually for our purposes of big O, say we want to know, well, how bad could it get? And in this case, we're going to be saying worst case. So we want to know, no matter how, as we get closer and closer to infinity, as we approach this seemingly infinite line over here as x tends off towards infinity, we want to know what's the worst we're ever going to have. So one way you could say this is you can say this with limits, and we'll get into that definition in a second because it's a little bit more confusing. But what we can also do is we can say, well, let's find two constants. Let's find a constant x0, and let's find a constant m. Oh god, that's really bad. But let's find these two constants, x0 and m, where x0 is going to be some point on our number line, like that, x0, and m is going to be some multiplier. So what we want to say is we want to say that f of x is equal to big O of g of x if the following condition is satisfied. And I'm going to, for all of my discrete math nerds out there, I'm going to say if and only if. Also 480 nerds, congrats. If and only if. Well, what do we want to say? Well, let's first take, for computer scientists, you're only going to be working with positive valued functions, but just to be safe, let's make it absolute value of x, f of x. And let's say that if f of x at some point is always less than or equal to m times g of x, well, then that means that this is big O of x. So for all x greater than or equal to x0. So it's just saying that once we hit past this point, every single value of g of x times m is always going to be bigger than f of x. And let's just draw out a function that would satisfy this on our little plot. So say we had some function that starts off really small here at the start, but then as we get closer and closer to x0, maybe it starts growing a bit, and then after x0, boom, it just spikes. And from x0 onward, our new function, let's say that this is m times g of x, our new function m times g of x is always going to be bigger than our initial function f of x. Now this is a lot of math jargon, so let's do out an example so it actually can make sense, make a bit of sense. And let's move this around a little bit. All right. Okay, we got kind of like a clear screen now. Let's do out an example. All right. So let's show that, say, f of x is equal to x squared plus 5, that's a squared, let's show that f of x is equal to big O of x squared, where again this just means that our g of x is equal to x squared. Well, how do we show this? Well, we want to find our constants. Let's find our constants x0 and m such that our condition is satisfied. Now, we have two constants that we can choose, so that actually gives us a large amount of flexibility. We want to say that x squared plus 5 is always less than or equal to mx squared, and then this is absolute value. And let's also just, for the sake of argument, say that x is greater than or equal to 1. That's the computer scientist in us that's telling us that. All right, so how are we going to do this? Well, one way is, maybe we can just bring the x squared over to this side, because x squared is not going to be, or x is not going to be 0, so we can do that. All right, so that means that, Control Z that. If we divide both sides by x squared, we'll end up with x squared plus 5 over x squared is less than or equal to m. That's an m. Let me redraw that. There we go. And we can break this fraction into two parts, which is 1 plus 5 over x squared is less than or equal to m. And now we can actually choose our value of x0. So depending on what our value of x is, so say x was 2, if we made that our m was, what's 1 plus 5 over 2 squared, that's equal to 1 plus 5 over 4, which is 9 over 4. So if we made our m, 9 over 4, that means that if we get bigger than 2, or even bigger than or equal to 2, that means that this inequality will be satisfied. So, and this all stems from the fact that, and you'll probably see this a lot, but, the 1 over x to the value of, to the raised to the exponent of p, is a decreasing function. So as you make x larger and larger and larger, this value is going to get smaller and smaller. So let's just say that, let's just choose x0 equal to 1. Let's just say that we want our constant to be make it so that our function is always bigger. So that would mean that 1 plus 5 over 1 squared must be less than or equal to m, which means that we can choose our m such that it is bigger than or equal to 6. So if we say x squared plus 5 is greater than or equal to 6x squared, well, in that situation, boom, this will always be the case. Plug in 1, you get, this is 6, and then if you plug in 2, you're going to find that our f of x looks, something along the lines of, if we start at 1, it's going to look something along the lines of that. And then if you look at our g of x, it's going to be something along the lines of this. I don't know, I'm just eyeballing it. But it's always going to be bigger. They're going to start from the same point, and this one's always going to be bigger. Now, interestingly enough, you can see that depending on the value of x0 you choose, you can get a smaller constant bound. And that's important for purposes of computer science when you're talking about, how slow does something run or how fast does something run. So that's something you might want to take into account. And you can see that, and let me bring it back to the color I had before, you can see that this expression right here, well, that has a limit of 1. So as we make x0 bigger and bigger, that means that we can choose m closer and closer to 1. So that's just an aside. But all of this right here implies that x squared plus 5 is actually, in fact, equal to big O of x squared. And I promised that before we go, because this is starting to drag on a little long, I promised before we go that I would talk about this in terms of limits, because a lot of you have taken calculus 1 actually, and well, calculus is easy for some of you, so maybe this will be an easier way of going about it. So we can also say that given some f of x, that is equal to big O of g of x, if and only if, oh Jesus, if and only if the limit, that is in fact how I normally write limits, I promise, the limit superior of, as x approaches infinity, of the absolute value of f of x over g of x is less than infinity. So if it comes out to be like some constant, or if it comes out to be 0, then this is fine. Now you might be wondering, what the heck is this thing over here? Joe, this is not calculus 1. What is a limit superior? A limit superior, in layman's terms, is just going to be like, if you have some function like this and then you have some sequence of points, it is talking about how often the sequence of points is allowed to go over your limit. But that's not important. For your purposes, we can say that this might as well be, and I'm going to piss off some mathematicians right here, we'll say that it's approximately the same thing as just saying that if the limit of the two is less than infinity, if you just take the limit off as x approaches infinity, and if it's less than infinity, then boom, bada bing, bada boom, you got yourself, oh crap, I almost ran out of space there, big O. And we can do that with our example that we just did in like 30 seconds, because hopefully everyone remembers their intro to calc. You know, we take the limit as x approaches infinity of x squared plus 5 over x squared, which is equal to, and I'll remove the absolute value signs, that's equal to the limit as x approaches infinity of 1 plus 5 over x squared, which is equal to, this goes to 0 as x approaches infinity, which is equal to 1, which is significantly less than infinity. It's not infinite at all. Therefore, dot, 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 f of x is equal to big O of g of x. All right, and just like that, you've learned about big O notation. Congrats, everybody. There we go, proved.